Let's try a few more chain rule problems. Talk about some other stuff, and then maybe we'll start talking about directional derivatives. This is not high. That's one. Co-17C. I'm like, what class is this? Okay. Today is the 17th. Reminder, no class on Monday, 3-day weekend, just in case anyone wasn't aware of that. Here's the attending form. So let's look at this example. Let's say we have given that z is equal to the inverse tangent of x squared plus 3y, and x is equal to s cubed times t, and y is equal to s times the natural log of t. And we're going to find all the partials of z with respect to the lowest level variables. In other words, we're going to find both del z, del s, and del z, del t. I'm not going to write it out, but I will point out that if you subbed in s cubed t for x and s times natural log of t for y, we can see that z at the very basic level is a function of both s and t. So I'll just point out that z is a function of s and t at the lowest level. But really, there's an intermediate path, right? Really, we have that z is a function of, careful here, x, which is a function of s and t, and y, which is a function of s and t. That's kind of really what's going on there. So the lowest level variables are s and t. Let's draw our mapping. So at the top, we have z. Z at the next level depends on x and y. And then the next level, x and y both depend on s and t. Now, here's what we don't want to do. We don't want to draw, I guess it doesn't actually really matter. We try to draw like the least amount of stuff, but I was about to say, you don't want to draw, I just would want to write it over here so we don't like, what I was going to say is, you don't want to draw something like this, where you have z depending on x and y, and then x and y both depending on s and t. But it actually doesn't really matter. Like you can totally draw it that way and be fine. And then you want to find all the paths to get you to s. So it'd be like del z del x times del x del s, and then del z del y times del y del s. But normally people don't draw it this way. Normally you don't draw multiple s's and t's at the bottom level. You just draw an s and a t down here, and then say, oh, x depends on s and t, and y depends on s and t. So we draw it like that. It's still representing the same sort of functional dependence. So writing out the formula for del z del s, that's all the paths from z to s. So each step along the path is a partial derivative. So from z to s, we can go through x. So it's going to be del z del x multiplied by del x del s. And then the other path that gets us there is through y. So del z del y multiplied by del y del s. I'll point out, and it should always look this way, that if you were to think of these as fractions, although they're technically not fractions, but they look like fractions. And the thing about the derivatives is like, they look like fractions. We often treat them like fractions. We multiply by the denominator like it's a fraction. You kind of operate with a thing in almost every way, shape, and form like it's a fraction, but it's technically not a fraction. But if you were thinking of this as a fraction and think about canceling the dx's, you'd be left with del z del s, which is what you should be left with if you're trying to find del z del s. If you think of the canceling stuff and the canceling doesn't look right, meaning you're left with something that's not what you have over here, then look back. So let's find all our partial derivatives. So z is equal to the inverse tangent of some stuff. I'll remind you all, it might have been a minute, that the derivative of the arctangent or the inverse tangent of x is 1 over x squared plus 1. So the derivative of the inverse tangent of some stuff is going to be 1 over the stuff squared plus 1 times the derivative of the stuff with respect to x, which is going to be 2x, times del x del s, which is going to be 3s squared times t. Plus, then we do del z del y times del y del s. So del z del y, same first step. The derivative of the arctangent of some stuff is also going to be 1 over that stuff, x squared plus 3y squared plus 1. But now we have to multiply by the derivative of the insides, and this time the derivative of the insides is going to be 3 because it's the partial with respect to y instead of with respect to x. And then we're going to multiply by del y del s, which is going to be 1 times the natural log of t. How do I feel about this? I don't think it's necessary for me to replace x with s cubed t and y with s natural log of t. It's a lot of writing that's not going to show you a whole lot other than that I could write it out. But if you wanted to write it specifically so that it depended on s and t, you would go ahead and replace each instance of x with s cubed times t and each instance of y with s times natural log of t. Let's do the other one. The nice thing about the other one is a lot of the work we've already done. So I want to find del z del t. Now I'm thinking of z as a function of t. So I'm going to find all the paths to get me from z to t. And again, not surprisingly, we have a path through x and a path through y. So that's going to give me del z del x to get me from z to x, multiplied by del x del t to get me from x to t, plus the other path, del z del y to get me from z to y, multiplied by del y del t to get me from y to t. I do think it's usually a good idea to write out the formula before you start taking partial derivatives. Not required, but a good idea. Some nice things to recognize here is we already know what del z del x is and what del z del y is. So we can just copy those parts without even thinking about having to take the derivative we get. Ow. Sorry. So del z del x is just this part right here. Nope, not just that part. It's this part right here. Sorry. It's all of that with the 2x included. And del z del y is all of that with the 3 included. So I'm going to get del z del x, which I'm going to rewrite it slightly so it takes up less space. I'm going to put that 2x on top and write it as 2x over x squared plus 3y squared plus 1 multiplied by del x del t, which is going to be s cubed times 1. Plus, now we look at del z del y, which we already know. Del z del y is right there. It's 1 over x squared plus 3y squared plus 1. And I'm going to write the 3 on top. All right, for that late change there. Times del y del t, which is the derivative of this with respect to t. So it's s times 1 over t, or s over t. And there's my del z del t. Always, if you have questions, you're welcome to ask them. I think these chain rule problems using partial derivatives are fairly straightforward, mostly. Yeah. It doesn't have to be just a function of two variables. You could have something like, sure, let's look at this. Let's look at one more example here before we do this other thing. So we could have something like, let me write some numbers. I try to number the things. Let's look at number 2 here. Let's say we have w as a function of x, y, and z equal to x e to the y over z. And we're given that x is equal to t squared, y is equal to 1 minus 4t, and z is equal to 3 plus t to the 5th power. And I want to find the derivative of w with respect to t. Which again, if we really, really wanted to, we don't, by the way, but if you wanted to, we could write w as a function of t as t squared e to the y minus 4t over 3 plus t to the fifth. That is not going to be friendly to us. If we should take, we could take the derivative of that, but you have to use the product rule, the chain rule again, the quotient rule. Like, it's just gross. So one of the reasons we're doing it this other way is because it's just easier. So don't do this unless someone asks you to like do it both ways. Instead, we're just going to say, well, great. W depends on X, Y, and Z. And then X, Y, and Z all depend on T. So it looks like there's going to be 1, 2, 3 paths to get me from W to T. Okay, question. Am I finding del W del T or dW dt? At the very base level, does W depend on one variable or multiple variables? At the basic lowest level. Can I write W as a function of just one variable or multiple variables? Just one, right? I can write W as just a function of T, which means we're not finding a partial derivative, we're finding the actual derivative of how W changes as T changes, because there isn't any other variable that's involved at the end of the day. So we're going to find dW dt. I feel like my D's and my del's don't look different enough, but oh well. It's probably actually a blessing, because then you'd be like, yeah, I wrote the thing I was supposed to write. So all the pathways. You should write down the 3, or I guess 6 things that we're going to be writing here. The 3 things are at, right? Go ahead and write down the 3 pieces that we're adding together. Each piece should consist of a partial derivative times a regular derivative. I'm going to give you 30 seconds. Write something. All right. So here are the 3 things we should be adding together. All the pathways to get us from W to T. So one goes through X. So we have del W del X times dx dt plus the next pathway, del W del Y times dy dt, and then del W del Z times dz dt. Again, del's because W depends on X, Y, and Z, so those are partial derivatives. D's because X, Y, and Z all just depend on the single thing T, so it's a straight derivative, not a partial derivative. Yeah. So the reason we're writing del W del X because at the first level, W is a function of both X, Y, and Z. So you can't just take a direct derivative. We have to take a partial derivative because there's more than one variable in play. So that's why we're writing del, because when we write del, which is a curlier D, that means we have a partial derivative because there's more than one variable we could be differentiating with respect to. On the other hand, we're writing dx dt because X is a function of only T. There isn't any other variable there. So it's not a multivariable function. It's a single variable function. And you don't take a partial derivative. We take a regular derivative. Right? Just there's a better word for just we take the derivative, right? Not a partial derivative. And that's the notational difference is partial derivatives get a curly D or called a del. Regular derivatives get a regular D called a D. Seem reasonable? Okay. So that, and also I will again stress, it is not that important. No one is looking that hard to make sure that your del's or your D's look like what they look like. I just want to be precise and correct for you all so I can say the right things. But if you weren't sure and you wrote a del instead of a D, you'd probably be totally fine. So I wouldn't worry too much about it. But again, it is good to know if you're taking a partial derivative or a regular derivative. So let's see what we've got here. Del W del X. So the partial of this with respect to X, great. We have X times a constant as far as X is concerned. So that's going to be 1 times e to the Y over Z multiplied by dx dt, which is 2t. plus del W del Y. Okay, the X constant hangs out. The derivative of e to the stuff is e to the stuff multiplied by the derivative of the stuff. The derivative of y over z, I don't really want to use the quotient rule here, and I don't need to use the quotient rule here. What I really have is y over z is just y times z to the negative first. And if I'm taking the derivative with respect to y, the z thing here gets to pretend like it's a constant, and the derivative of y times the constant is just 1 times the constant. So I'm going to get 1 times z to the negative first. Plus del w del z. Sorry, hold on with my plus there. I forgot my multiplication. So, right, so actually let's label things here. Let's be smart, James. So here's my del w del x. Here's my dx dp. Here's my del w del y. And I've forgotten my dy dt, which should be -4. Squeeze that in there. Sorry about that. And it's terrible. Finally, plus my del w del z. So if I'm differentiating this with respect to z, the x constant hangs out. The derivative of e to the stuff is e to the stuff times the derivative of that stuff, and the derivative of y times e to the negative first is going to be y times the derivative of z to the negative first is -1 times z to the negative second. That's my del w del z. And then we have to multiply by dz dt, which is going to be 5 times t to the fourth. Sorry, I said dz dt is what I should be having there. I think I might have said the wrong thing earlier. Sorry, dz dt there.
What is the dy dt say?
It's at the -4, and there's a plus sign right after it that's connecting us to the next piece. Yeah, sorry, I know it's a little gross there. And then again, I won't do it, but I'll point out that if you want, maybe I will do it. It's kind of terrible. Sure. So if I wanted to write this, if I want to write dw dt in terms of just t, we would replace every y, z, and x with what they're equal to. So we would have something gross like e to the 1 minus 4t over 3 plus t to the fifth. I'm regretting this choice already. Times 2t plus my x, which is t squared. You probably don't need to write this down. Times e to the same thing, 1 minus 4t over 3 plus t to the fifth. Times z to the negative first, which is 3 plus t to the fifth to the negative first. Times -4, oh my gosh. Finally, plus the last piece here, which is going to be, I need more room down here, x, which is t squared, times again, e to the grossness, 1 minus 4t over 3 plus t to the fifth, times y times -1 times e to the negative second. So y is 1 minus 4t times -1 times z to the negative second times 5t to the fourth. I did no simplification, right? I just wanted to write it out in terms of t. So there you can see, oh, look, the derivative dw dt is in fact a function that just depends on t. So it makes sense to write it as a regular derivative. But most people are totally fine with leaving it like this because we know every one of us could plug in all those things for the x, y's, and z's and see what it looks like. It's not like a big step. It's just a pain to write out. Cool. Let's do a few more things with the chain rule. And then we'll probably move towards the next thing. So this next question, I think, is more of an example of a question that comes up kind of in web work problems, but I could see it being asked as like an exam question. So we'll give ourselves one of these. So let's look at this problem. We're going to be given the following situation. Given that z is equal to f of x comma y is differentiable. This means we can take its derivatives. And we're given the following. X is a function of t. Y is also a function of t. So x is equal to g of t, y is equal to h of t. And we're told that g of 3 is equal to 2. H of 3 is equal to 7. G prime of 3, the derivative of g at 3 is equal to 5. h prime of 3 is equal to -4. And finally, pardon me, the partial derivative of your function z or your function f, whatever you want to call it, with respect to x, evaluated at 2 comma 7 is equal to 6. And your partial derivative of f with respect to y, evaluated at 2 comma 7 is equal to -8. Given all this information, we're then going to be asked to find the following. Find dz dt when t is equal to 3. So we can make a map. We should make a map. Whenever you have these multivariable functions that have multiple levels, it's almost always a good idea to draw the mapping. So the very top level, z, or if you want to call it f of x, y, is our top level thing. Usually there's only one thing at the top, right? Your function depends on multiple things. And then at the next level, z or f, whatever you want to call it, depends on x and y, right? We're literally writing f as a function of x and y. And then at the next level, we can see that x is written as a function of t, and y is also written as a function of t. So we have a usual kind of diamond-shaped map, which it comes up a lot. So let's write out what we should get for our derivatives here. We're going to say that dz dt is equal to, you can either write z or f. They're kind of interchangeable. But since we wrote the notation, since they gave us the notation here in terms of x, I'd probably write del f del x instead of del z del x to make it easier for me to understand what's happening. So I'm going to say this is going to be from f to x, del f del x times dx dt plus del f del y times dy dt. And we're going to plug in t equal to 3. Okay, important to note. If t equals 3, then x is equal to g of 3, which is going to be g of 3, which is 2. And y is going to equal h of 3. And h of 3 we were told is 7. So we want to find del f del x. Another way of writing that is fx evaluated at the inputs. Well, the inputs to the function f are an x and a y value, which are 2 and 7. dx dt, or in other words, g prime, right? That if x is equal to g, dx dt is equal to the derivative of g. That's going to be g prime of, I'm going to plug in my t value, which is 3. Same deal over here. Del f del y, I'm going to write as fy evaluated at the xy values, 2 and 7. And then dy dt is just another name for h prime of t, or h prime of 3 if I plug in the values. And then we just look at our table to see what we've got. fx evaluated at 2 comma 7 is 6. G prime of 3 is 5. Plus fy evaluated at 2, 7 is -8. And h prime of 3 is -4. So end up getting 30 plus 32, which is 62. Nowhere were we told what the function was or any of the derivatives were. We just were given all this information at this one particular value or place and then found all of it based on that. Again, I don't think this is a super realistic question, but sometimes people like to ask things like this. And there definitely are web work questions like this when people teach us class using web work. I don't think there's any homework questions like this. I don't think. I didn't look extensively though, so there could be. Okay. So the other thing people sometimes do with this, and there definitely are homework problems that get at this next point, is, I'll just write the words, the chain rule that we've just learned can be used as a shortcut for implicit differentiation. I know it's been a little while since we talked about different implicit differentiation. I think because that's something we learned back in the first quarter of the 17 series. But let me remind you. So if we were given the following, we were given, say, x cubed plus y squared plus x e to the y equal to 7, and I said find dy dx, we would differentiate this whole thing with respect to x, pretending like y is a function of x, and then afterwards we'd solve for the derivative. So let's do that. So the derivative of x cubed is 3x squared. So an important thing to remember here for this one moment is we are not in the partial derivative sense where we're like pretending like x is a variable and y is a constant. We're pretending like x is a variable, well, not pretending, x is a variable and y is a function of that variable. So when I take the derivative of a y squared or a function squared, I get 2 times y to the first multiplied by the derivative of the insides, which is dy dx. And then for the derivative of x multiplied by e to the y, we have to use the product rule. The derivative of x is 1. We leave e to the y alone. We switch it up. We leave x alone. The derivative of e to the y, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Equals not 7, but the derivative of 7, which is 0. It's really important there. People, for some reason, often forget to take the derivative of that and just leave it at 7. Nope, the derivative of 7 is 0. Okay, so now we're going to solve for dy dx. So we'll leave these things on this side, subtract those things to the other side. Also, I'm going to factor out the dy dx while I'm at it. So I'm going to have dy dx multiplied by 2y plus x e to the y. And on the right-hand side, I'm going to have a negative 3x squared minus e to the y. Which I'm actually going to factor out the minus sign there. I wouldn't usually do that, but I want to do it here because I want you to see something. So that's going to tell me that dy dx is equal to negative 3x squared plus e to the y over 2y plus x e to the y. Cool. We're going to do it again, but in a totally different way. So here's the idea of how we're going to do it using the chain rule. So we're not going to go through this process every time, but we're going to do this process one time. So we're actually going to rewrite this just a little bit. We're going to bring everything to one side. So we're going to say, we're going to let our function of x and y, we're going to call it capital F, is going to equal one side of this equation that's equal to 0. So it's going to be x cubed plus y squared plus x e to the y minus 7. And we know that that expression should be equal to 0. So now what we're going to do is we are going to pretend like, do I want to say that? I'm sorry. This is something I always have to like wrap my brain around the right way for a second. Yeah, that makes sense. Yes. Okay. So let me draw this one. Let's draw a map here. So I'll point out that our function f depends on what two variables? X and y. But I'll also point out that we are making the implicit assumption that y depends on x. Right? That's usually what we do when we're doing implicit, where we're all like, oh yeah, we're pretending like y is a function of x. So if we take the derivative of both sides here, the derivative of f, well, I should say, yeah. Okay, sorry. So we're going to take the derivative with respect to x of both sides. When I say both sides, I specifically mean this side and this side. So the derivative of f with respect to x, well, there's two paths that get me from f to x. There's either the path that goes straight to x, or there's the path that goes through y. That's going to be fy multiplied by dy dx. On the right-hand side, help me out. What's the derivative of 0? Right. Okay, the reason we're doing this is then check this out. We can solve for dy dx. I'm going to subtract fx, the partial derivative to f, and divide by fy. So another way we could have found dy dx is by getting negative the partial with respect to x divided by the partial with respect to y. But check that out. If we do this, look what we get. If I take the partial with respect to x, I'm going to get 3x. So now we're back in the framework where we are thinking of x as its own thing, y as its own thing. So if we take the partial with respect to x, we're pretending like y is a constant. So taking the derivative with respect to x and leaving the y's kind of out of it, we're going to get 3x squared plus 0 plus 1 times e to the y plus 0 divided by the partial with respect to y, which is 0 plus 2y plus x times the derivative of e to the y is e to the y minus 0. Hey, look, it's exactly the same. Not even a little bit different. Exactly the same. So the sum up here is that if you want to find the derivative of some equation implicitly, instead of doing the normal implicit differentiation process that we learned in 17a, we can essentially set our whole equation equal to 0 and then just take the partial of the independent variable over the partial with the dependent variable and put a minus sign in front of it. And this kind of works for however many variables you want. Here's what I mean. I should also point out this is equation 4 in your textbook. So there are a couple problems that say use equation 4 to do this thing. This is equation 4. And equation 5 is essentially the same thing, except it's with partial derivatives instead of regular. Like it's with functions of more variables essentially. But the what's the word I'm looking for? The formula or the formula's not quite right, but the formula is essentially the same. I'll tell you what I mean in a moment. Let's do one more example here. So if I was given, all right, let's just write it out. So we're going to say find dy dx for x cubed times y to the fourth equal to 3 minus x times cosine of y. And before you just start going and doing this, there is one thing you have to do first. You have to rewrite it so everything is on one side. So the whole thing's equal to 0. Technically, it could be everything but a constant on one side. So if you really, really wanted to leave that 3 on the right-hand side, you could, but let's not. So we're going to rewrite it as f of x comma y is equal to all the stuff brought to pick whatever side you like. I'm going to pick the left side generally. So x cubed times y to the fourth plus x times cosine of y minus 3 equal to 0. And then instead of like deriving the formula again, we're just saying, great, we know that the derivative dy dx, and here's how it always works. The variables swap places in the quotient. So instead of having x on the bottom and y on the top, it's going to be y on the bottom and x on top, but it's the partial derivative. So it's going to be the partial of x on top, the partial with respect to y on the bottom, and then it's the negative of all that. So let's see, that's going to be negative. The partial with respect to x is going to be 3x squared times y to the fourth plus 1 times cosine of y. And the partial with respect to y on the bottom is going to be x cubed times 4y cubed. I'd probably put the 4 in front, but I won't. Plus x times the derivative of cosine of y is negative sine of y. So minus x times sine of y. Much faster, in my opinion, than actually taking the derivative of both sides with respect to x and then solving for dy dx. But yeah, I was going to say but there's really no but there. If someone asks you to do it this way, they really want you to do it that way. So some of the problems in the textbook say use this formula or the alternate version, which we'll talk about right now, to find the derivative implicitly. Let's look at one. Yeah, I got one more. Yeah. So it works no matter how many variables you're using. So for example, if I gave you, say, x squared plus y squared plus z squared equal to 3 times x times y times z. And I said, find del z del x. Well, it's going to be the same formula. Negative out front. Yes, there's one more thing I have to do first, but I'm going to write this part first. Okay. What goes on top? The partial with respect to what? X. What's going to go on the bottom? Partial with respect to not y, z. So whatever variable is there goes there, whatever variable is there goes there. I did kind of skip the step of rewriting it as something equal to 0. So I should rewrite this as f of x, y, z equal to x squared plus y squared plus z squared minus 3xyz equal to 0.
Is it always negative?
Yes. Say it one more time. Say it one more time. Yeah, exactly. Right. Because exactly, because you're subtracting things over to the other side, which is what introduces the negative sign.
If the other side is all negative, would it be positive?
No, it would just be the negative of that negative thing. So the negative always has to be there to change the sign of whatever you have, because whether it's negative or positive on the side it's starting on, it's moving to the other side, becoming the opposite sign of what it was, whether it started off with negative or positive. So here, what we're going to get is negative. Let's see, fx is the partial with respect to x, so it's going to be 2x plus 0 minus 3 times 1 times y times z. On the bottom, fz is going to be 0 plus 0 plus 2z minus 3 times x times y times 1. And in a similar way, you all right now should find del z del y. So go ahead and do it. Find del z del y. Do that. So we should get negative fy over fz. Fy is going to be 2y minus 3xz. And fz is the same as it was before, 2z minus 3xy. I will point out this one has a lot of symmetry in it, so maybe not like as interesting as some other problems, but that's just because of how the problem's written. And I think that's pretty much all there is to really say about the chain rule. So let's continue on to the next section to help prepare you for talking about directional derivatives on Monday, I imagine. Where the papers go. I don't know. I'll find you later. Sure. Directional derivatives. So I will point out up until this point, we have only found derivatives in two different directions. In the x direction and in the y direction. But if you're on some point on a surface, you can find the slope of that surface in any direction, right? It doesn't have to be in the direction moving towards you or the direction moving to the right. And there's a very straightforward, probably not the best word. There's a way to do this with not too much terribleness. So let me remind you of a couple things. Thing one, the dot product. So if we have two vectors, u and v, and the angle between them is theta, then there's two ways of finding the dot product. One way is that u dotted with v is equal to the length of u times the length of v times cosine of the angle between them. And we'll also remind you, because it's important, that if the dot product of u and v is equal to 0, that means the angle between them had to be 90 degrees, because cosine of 90 degrees is equal to 0. So if the dot product is 0, then the angle theta is 90 degrees. In other words, they are perpendicular. But that's not the way we usually calculate the dot product. If we were calculating the dot product, we usually do it using the component form. So if we were given, for example, that u is equal to, say, the vector 1, 4, I should write, this is an example here, and v is equal to the vector 5, 2, then the nice, easy, right, finding the angle between these vectors is terrible. The way you actually want to find the dot product is say, okay, great, u dotted with v is equal to 1 times 5 plus 4 times 2. You multiply the corresponding components together and add up all the results to get the scalar 5 plus 8, which is 13. I will also point out, just because I think it's good to know, the dot product is also called the scalar product, because it takes two things that aren't scalars, vectors, and combines them together in a way that produces a scalar number. So when you dot two vectors together, the output isn't a vector, it's a number. Could be positive, could be negative, could be 0. Okay. And then I feel like we didn't talk about this last quarter, but we need it right now. So yeah, I can make this work. So I want to talk about, for just one brief second here, the parametric equation of a line in 3 dimensions. So the problem is, in 2 dimensions, a line is really easy to write the equation of. You got a point, you got a slope, y minus y1 equals the slope times x minus x1. In 3 dimensions, you can't really do that. What we need is a point. Instead of a slope, you need a direction, aka a vector. So to be able to fully write the equation of a line, we need a point and a vector. Okay, so let's say we have this line, L, and it goes through these points, 1, 2, and 4, 7. And yes, we totally could use the y equals mx to b form and do it that way, but I'm gonna do it differently. Instead, we're going to say, well, imagine there's a particle moving along this line, and at time equals 0, it's at this first point, 1, 2, and 1 second later, it's at this second point, 4, 7, and it keeps traveling in the same direction. So if I wanted, I could say that another second later, well, from time equals 0 to time equals 1, the x value increased by 3, and the y value increased by 5. So I imagine later on, if it keeps going in this direction, if x increases by 3 again, I'd be at 7, if y increased by 5 again, 12. Because if we're traveling along a straight line, we always have this nice kind of just way that it works. So we could say here, the parametric equations are that x is a function of t is equal to 3 times t plus 1. Right, because we know that every time t increases by 1, x is going to increase by 3. But when t equals 0, x should be 1. And y of t should be how much times t? 5 times t, because y is increasing by 5 every time, plus 2. And these are the parametric equations. This is not super important, but it's going to help us see the thing we want to see. So that's why we're talking about this real briefly here. Yeah. Trying to make sure I get there so I don't leave you all hanging. So let's go back to our example of the mountain that we talked about a few classes ago, where we have f of x comma y equal to 9 minus x squared minus y squared, which looks like this. And on that mountain, we specifically had talked about the point 1, 2, 4. About right there. So there's the kind of side view, and let's draw the top view as well. So if we look at the top view, of that red circle there, the x coordinate, y coordinate are 1 and 2, respectively. So I can't quite see that very well. So here's the question we want to be able to answer. Suppose you're at that point, and instead of moving in the x direction or in the y direction, I want to move in the direction of the vector 4/5, 3/5. So I want to move in the direction of over 4, up 3, essentially. So kind of like, it's not quite that way. It's more like that way. I want to move that way. Sorry, I know that I always write that 1, 2 in the wrong spot. Like, and whenever I've done this process, I'm always like, oh, good job, James. You wrote the 1, 2 in the worst possible spot. Let's write it right there instead. Sorry about that. And this vector here is the vector where we're going over 4/5 and up 3/5. I will point out that that is a unit vector. It has a magnitude of 1. Typically, when we do this, we do like our vector to have a magnitude of 1. If it doesn't, we usually scale it down so it does. But not something we need to focus on right now. So we're going to parameterize the line that passes through the point 1, 2 in the direction of the vector 4/5, 3/5, which isn't too terrible. Something like that. So here's what we're going to get. Our x coordinate is going to be given by, well, at time equals 0, we want the x coordinate to be 1. So it's going to be 1 plus, then it's just going to be however much the x coordinate of this vector is. It's going to be 1 times 4/5, plus 4/5 t. Just like in the previous example, it was the coordinate plus however much the vector was increasing it by. And the y coordinate is going to be 2 plus 3/5 t. Okay, we're almost there, I promise. So now, here's what we're going to do. We're going to find the slope, aka the derivative of the function f of x comma y in the direction of this vector v. We'll check this out. F depends on x and y, and x and y both depend on the variable t. So df dt is equal to del f del x times dx dt plus del f del y times dy dt. Which ends up being, let's see, del f del x is negative 2x. Actually, I don't want to write it that way. So here's how I actually want to write it. Sorry, I'm getting ahead of myself a little bit here. So I'm going to point out that we can write this as a dot product. It's the dot product of two vectors. The first vector is del f del x, comma, del f del y, the vector of partial derivatives of your function, which is called the gradient. And then the other one here is dx dt, comma, dy dt, which I'll point out is literally the vector v. So if you take the derivative of x, what do you get? You get 4/5. You take the derivative of y, what do you get? You get 3/5. So this ends up being what we call the gradient of your function, which is an upside down triangle, that's called the gradient, dotted with the vector that you're going in the direction. And that is how you calculate the directional derivative in the direction of some vector. And then you would plug in the point. So in this example, I know it's 2 o'clock. I'll wrap it up here real quick. So I'll point out here that in this example, my gradient of f would be the vector negative 2x comma negative 2y. And at the particular point of interest, which is the point 1 comma 2 comma 4, I'm plugging in 1 for x and 2 for y. So if my gradient of f evaluated at 1 comma 2 is going to be negative 2 comma negative 4. My vector v, again, my vector v is literally just the derivative of x, which is 4/5, comma the derivative of y, which is 3/5, or the vector they gave us in the first place. So our vector v here is the vector 4/5, comma 3/5. And then if we dot these two vectors together, the gradient of f dotted with v is going to be, sorry, no, I'm squeezing this in, negative 2 comma negative 4 dotted with 4/5, comma 3/5. We're almost there. Negative 2 times 4/5 is negative 8/5, plus negative 4 times 3/5 is negative 12/5. Adding that together, we get negative 20/5, which is negative 4. And what that tells us is that from this point, instead of moving in either the x direction or the y direction, if we move in the direction of the vector 4/5, 3/5, which is kind of like that way, if you move down the mountain, your slope is negative 4. If you move from that point in that direction. That's what the directional derivative tells you. It tells you the slope of the surface from a certain point in a certain direction. And you calculate it by just finding the dot product of the gradient with the directional vector. That's the directional. We'll definitely talk more about this on Monday, but I wanted you to see it before you start in class because I think it can be a little bit confusing. And we'll definitely do more examples on Monday. I will point, the last thing I'll say is that directional vector v does need to be a unit vector. So if it isn't, we divide it by its own length to make it a unit vector. But again, we'll say more about that on Monday. I'll make sure you get the sign-in sheet if you didn't already. I think the two of you both didn't get it. So if you could pass that forward, I would appreciate it. And I have office hours over in Centro. And have a lovely 3-day weekend. I will not see you on Monday. I'm a liar. I'll see you on Wednesday because we don't have class on Monday. Yes, someone just wrote, no, not Monday, Wednesday. Yep, exactly. See you all on Wednesday, not on Monday.